Hello everybody. In this video lecture, we will cover the chemical level of organization, and I will use PowerPoint that will help me out to cover this topic. So this is the PowerPoint that I will use, chemical level of organization, and I will record two videos because I don't want them to be very long. So it will be part 1 and part 2. So let's go ahead and begin. And I will pick up my pointer. So anything that has mass and occupies space, we call matter. We have 3 states of matter. It can be solid, liquid, and gas. Solid means this matter has defined shape and volume. Liquid has defined volume and changeable shape. And gas has both changeable shape and volume. So you can see here on these diagrams, when we're talking about solid, then we have fixed volume. When we're talking about liquid, we do have fixed volume, but it can change the shape. And when we're talking about gas, it can change both shape and volume. And energy is capacity to do work or put matter into motion. The whole universe is made of matter and energy. The major two types of energy are kinetic energy and potential energy. And kinetic is energy in action, potential is stored or inactive energy. So in this diagram over here, you can see how one type of energy, potential energy, can be transformed into kinetic energy. And you're comparing here your car and your cell. Like for car to move, we need gas. And what gas has stored potential chemical energy. This chemical energy is stored inside chemical bonds of the molecule, octane, that is found in the gasoline. So you have this molecule, and molecules are made from atoms that are connected by chemical bonds. So inside those chemical bonds, molecules have potential energy. So in the presence of oxygen, those chemical bonds can be broken through reaction. It's called combustion reaction. And then energy from chemical energy, potential, can be transformed into kinetic energy of movement. And of course, it will be some waste product in the, that is poor in chemical energy. And a waste product in this example is carbon dioxide and water. But your cells also need source of energy to perform all cellular function. Your cells actually need ATP, right? And to get this ATP, your cells using also potential chemical energy. Glucose, in the presence of oxygen, glucose is broken and ATP is synthesized, right? So again, this we have potential energy that is transformed in another really potential energy, but in a different form, and then ATP can be transformed into kinetic energy. And waste product are the same, carbon dioxide and water. So this process is called cellular respiration. So energy cannot be created or destroyed. Energy may be converted from one form to another form. So this is the first law of thermodynamics. And it's so amazing that energy cannot be created and destroyed. Just sometimes you think about it and it's mind-blowing. If it cannot be created, where this came from, right? Okay, but anyway, when we can convert one form of energy into another form of energy, but this conversion is inefficient because some of energy is lost as a heat. Of course, energy cannot be lost. The amount of energy in universe is constant, but it's lost as a usable energy. So this part of energy as heat cannot be used anymore to carry on any chemical reactions. Composition of matter. Matter is made of elements. What are elements? Elements are part of matter that cannot be broken down by ordinary chemical means. That means if I have element of gold, there is no any chemical reaction that I can perform to make, let's say, carbon from gold. Or if I have oxygen, there is nothing I can do chemically to make, let's say, hydrogen from oxygen, right? That's elements. So each element has unique properties. It has physical properties, and physical properties are detectable with our senses or are measurable, and chemical properties. Chemical properties are how atoms interact or bond with one another. So atoms have atoms have atomic symbol, right? So right over here, shown the carbon. It's usually one or maybe two letter for each element, and each element will have atomic number and atomic mass. And you can find this information in the periodic table of elements. So atoms are unique building blocks of each element. So element carbon is made from carbon atoms. Element gold is made from atoms of gold. Major elements of human body that make up about 96% of body mass are oxygen, carbon, hydrogen, and nitrogen. It's also amazing to think about it. Your body looks so incredibly complex. And when you start thinking that 96% of your body are made from only 4 elements, I don't know, for me, it's kind of like, wow, that's interesting. So how you can make complexity from 4 elements, pretty much. And about 4%, because we have here, look, 96, right? So it's a little bit less than 4% are elements such as calcium, phosphorus, potassium, sulfur, sodium, chloride, magnesium, iodine, and iron. And less than 0.1% are elements that we call them trace elements, but they still required for proper body function, even despite the fact that we have them in so small amount. So those are trace elements. So you can see all of them over here, pretty much. So what are chemical bonds? Well, chemical bonds are interaction between atoms. And we know that atom, so here we have a sodium and fluoride atoms, and atoms, they have a nucleus. So here inside, and in the nucleus, we have protons and neutrons. And then atoms have electrons, and electrons are surrounding the nucleus. And the element is stable when it has his outer shell, right, outer shell fulfilled. And to fulfill the outer shell, atoms require 8 electrons. We call those electrons valence electrons, and they're located on a valence shell. So the outer shell of an element is a valence shell, and atoms, they have different number of electrons, but they're stable if they have 8, except of a very first shell, and the first shell can only carry or support 2 electrons. So only 2 electrons can be found in a first electron shell or energy level, and all the other shells can have 8. Now, types of chemical bonds, ionic, covalent, hydrogen, those are just few that are important in biology and biochemistry. So ionic bonds are usually between metal and non-metal. Covalent bonds are usually between non-metal and non-metal, or metalloid and non-metal. So ions are formed by transfer of valence shell electrons between atoms. Let me see if I have a picture over here. Look, so for example, if we have sodium, right? So sodium has, okay, so 11 protons. So that means it has, no, it will have 11 protons. So that means we have 11 electrons, right? Because atom has as many electrons as protons, right? So 11 protons, 11 electrons, the number of neutrons can vary. So sodium has 11 electrons, and if you see the first energy level is complete, 2 electrons. The second one is complete, 8 electrons. And the last shell or energy level is not complete. Sodium has only 1 electron. So the sodium has tendency to lose this electron to achieve this perfect energy state, right? So sodium wants to have, well, it doesn't want anything, but it's stable when it has 8 electrons on the outermost shell, right? So sodium has tendency to lose this electron. If you look at the chlorine atom, and chlorine atom has 17 electrons, so the first shell is complete, the second is complete, the third one is almost complete. It's just missing 1 electron. So chlorine has tendency to accept extra electron to achieve this perfect energy state, right? State of noble gas. Now, when sodium loses its electron, it became positively charged ion, because electrons are negatively charged. When we have neutral molecule, we have 11 protons. Protons are positively charged, and 11 electrons. Electrons are negatively charged. So this atom is neutral. 11 positive particles cancel out 11 negative particles. But when sodium is losing 1 electron, it became positive. So it became a positive ion. So it became sodium ion. We call it cation. Now, when chlorine accepts 1 extra electron, right, over here, now it has 17 positive charges and 18 negative charges. So it's also become ion, but it's a negatively charged ion. So it's a chloride ion, and it's anion. And now we have positive ion and negative ion, and they attract each other. And this attraction is called ionic bond, right? So in this situation, chloride ion, because chlorine is more electronegative atom, so it has better affinity for electrons. So it's gonna steal this electron from sodium and became negatively charged ion, right? So that's how ionic bonds are formed. So let's see what we skipped over here. So anions are negatively charged, and they are formed when atoms gained 1 or more electrons. cations, they have positive charge, and those atoms, they have lost one or more electrons. And attraction of opposite charges result in ionic bond, right? So here's the ionic bond. So I think I skipped one slide. Now, covalent bond. Covalent bond are formed by sharing of two or more valence shell electrons. And it allows each atom to fill its valence shell at least part of the time. So over here, you can see the formation of covalent bonds. And we have hydrogen atoms and carbon atom. So if you look at hydrogen, hydrogen has only one shell, and it's not complete because we need one more here. Hydrogen needs 2 electrons on its shell to achieve this state of noble gas, so to be stable. Carbon need actually 4 electrons. So what happened over here, carbon share its electrons with 4 atoms of hydrogen, right? So, and forming the simplest organic molecule that is called methane. So this is methane, CH4, and it's the simplest organic molecule because organic molecules are molecules that have carbon and hydrogen. So this is a molecule of methane gas, and this is structural formula that shows single bonds between carbon and hydrogen. So those lines represent covalent bonds. And covalent bonds means that 2 atoms share their valence electrons, and it allows them to fulfill their outer shell at least partially at a time, right? So not all the time, because, you know, sometimes those electrons will be kind of on this side of hydrogen, but at least partially they fulfill their valence shell. When we're talking about covalent bonds, atoms, they can share more than just 2 electrons. They can share, for example, over here, 4 electrons. Then this would be the structural formula, so it's a double covalent bond. Or they can even share 6 electrons, and this is how structural formula would look like, and it's a triple covalent bond. So when atoms share electrons, when they form covalent bonds, this sharing may be equal or unequal. So equal sharing produces electrically balanced non-polar molecule. Example would be carbon dioxide, CO2. So because carbon and oxygen, they really similar in their electronegativity. So they attract electrons with the same force, similar force, right? And that's why they share electrons equally. And this molecule would be linear and symmetrical, right? And so this is how it would be represented. Carbon shares over here 2 pairs of electrons, or 4 electrons, with each oxygen atom, and this molecule is non-polar. Covalent bonds, however, can be polar covalent bonds, and this happens when atoms share their electrons not equally, right? Unequal sharing by atoms with different electron attracting abilities produce polar molecule. So the example would be a water molecule. Oxygen is more electronegative atoms. It means it has higher attracting ability for electrons. And hydrogen will have lower attracting ability for electrons. that's why electrons will spend more time close to oxygen than they spend next to hydrogen. So oxygen will have kind of like partial negative charge. It's not real negative charge, that's why we use this sign. It's partially negative. And hydrogen will be partially positive. And result would be V-shaped water molecule that has two poles. So this pole is positive, this pole is positive, and this pole is negative. And this is called the polar molecule. Now here you can see this summary, right? When we have non-polar covalent bonds, then we have equal sharing of electrons, and charge is balanced among atoms. So that's our carbon dioxide example. Or we can have polar covalent bonds when sharing of electrons is unequal, and then a molecule has slightly negative and slightly positive ions. An example would be water. And here we have ionic bond, where we have complete transfer of electrons from one atom to another atom. And this would be example of sodium chloride. So it kind of like, you can see like ionic bonds are really like strongly polar covalent. I think in the chemistry now, they even do not have this division between covalent and ionic, because the principle is the same. The more negative one of the atom is, the stronger is attraction between this atom and electrons. And finally, this atom can steal electrons completely, forming ionic bonds, right? So ionic bonds, we have ions that are attracted to each other. Covalent bonds, we have atoms that share their electrons. Now, what are hydrogen bonds? Hydrogen bonds are attractive force between electropositive hydrogen of one molecule and electronegative atom of another molecule. An example would be hydrogen bonds between water molecules. But we also have hydrogen bonds in large organic molecules, for example, in DNA and in proteins as well. So over here, you can see we have several water molecules. Water molecule is polar. So one pole is slightly negative, another is slightly positive. And because of this, there is some attraction and interaction between a negative pole and positive pole. And this is what hydrogen bond is. And hydrogen bond is a very weak bond, and it's indicated with dotted line. Now, what are chemical reactions? Chemical reactions occur when chemical bonds are formed, rearranged, or broken. So we just talk about the atoms and how electrons of the atoms interact with each other, right? So we have atom of carbon and atom of oxygen, and their outer electrons interact, forming molecule of carbon dioxide. So they're forming these covalent bonds. Now, when we break this bond, rearrange them, or form, that's what chemical reaction is. And chemical reactions are represented as chemical equations. And chemical equations contain molecular formula for each reactant and product, and relative amounts of reactants and products which need to be balanced. So over here, we can see two examples of chemical equations. And we have chemical formula for reactants and for the product. And over here, and here we balance it, because law of conservation of matter tell us that if we have 4 atoms of hydrogen in the product, we need to start with 4 atoms of hydrogen as reactants, right? So 4 hydrogen plus carbon, give us one molecule of CH4, that is methane. So you can see what happened over here. Chemical bonds are formed, right? Chemical bond is formed between carbon and 4 atoms of hydrogen. So formation of this chemical bond give us a molecule, and we call it chemical reaction. And the same over here, we form chemical bond, covalent bond between 2 hydrogen atoms, and we get a molecule of hydrogen, right? Formation of bond is called chemical reaction. Or we can break those bonds, right? If you go opposite side, we can break this bond, and it's also will be chemical reaction. So all chemical reactions are either exergonic or endergonic. Exergonic reactions, they release energy, and endergonic reactions, they store energy. And exergonic reaction in biology are called catabolic reaction, and endergonic reaction called anabolic reaction. So catabolic, when you break large molecules into smaller and energy is released, and anabolic, when you bind smaller parts to make larger molecule and energy is stored inside those chemical bonds. So over here you see the representation of endergonic reaction and exergonic. So here we have reactants, and reactants, they always have some energy stored inside them, right? So they do have energy. Then we need some activation energy, and we get a product. And you can see that product, the end product has more energy, right, over here than reactants. So what does it mean? It means that this energy, we store energy inside this product. Energy is absorbed. Now, if over here we have reactants, and here's our products, and now products, they have less energy. That means some energy was released, right? And that's why this reaction, we have anabolic reaction because we're building something, right? We're storing the energy, and this is catabolic reaction. Now, what is metabolism? Metabolism are all chemical reactions that take place in the organism. And 2 parts of metabolism is catabolism and anabolism. So catabolism is energy yielding mechanism, and anabolism is biosynthetic mechanism, right? So and what connects these 2 parts of metabolism is actually ATP. Because what catabolism does in your body, it actually releases energy, and this energy is used to synthesize ATP. Now for anabolism, if you need to build something from nutrients, you need to build big polymers, you need to use this energy, right? And you use this energy, and then you need to renew the store energy that you have in your body, right? So if you're using energy, you can finally get to the point that you don't have it anymore, right? If you're always using ATP, let's say you're a little baby and you're growing, you constantly grow, right? And you're using ATP for growth. At some point, you like, where's my ATP? There is no more ATP available. So you always need to rebuild it, restore the amount that you need for normal functioning. And that's you using energy from catabolic reaction, right? Catabolism, if you want to put it really easy, right? Catabolism, you eat your food, right? And you get energy from your food. And anabolism, for example, you're growing or you're building your muscles, and you get this energy from your food to build your muscles. It's way more complex than this example that I gave you. But it's kind of just give you a main idea what catabolism and anabolism is, right? So you eat your food, So you can break this food through catabolic reaction and get energy from your food. And you can use this energy to build your body, right? You can also use this energy for movement, for your heart to contract, for your kidneys to function. That's, of course, also very, very important. Okay, so anabolic reaction, we're building something, right? It's a joining of small molecules to form larger ones, complex molecules. So it's a growth process. Example would be dehydration synthesis reaction. Dehydration synthesis. Synthesis means we synthesizing something, we making something bigger. Dehydration means at the same time we losing water, because dehydration is losing water. So water is formed during dehydration synthesis reaction. So what would be example? Glucose plus glucose would give you glycogen. So your cells of your muscles or your liver cells, they store glucose in the form of glycogen. To do it, they need to form chemical bond between two molecules of glucose, and that's dehydration synthesis reaction. Or your adipose tissue, your adipocytes can attach 3 fatty acid to a glycerol molecule to make a fat. So this is a simple fat called triglyceride. Also, for example, if you build your muscles, but not necessarily muscles, you can produce like different enzymes as well, right, and hormones. But let's say you're building your muscles, so you need a lot of protein. Polypeptide is a protein. Your cells gonna form chemical bond between amino acid forming polypeptide. Or when your cells divide, first you need to replicate your DNA, so you need to make this nucleic acid. So your cells gonna connect nucleotide to make nucleic acid. So you can see how we go from simple molecule to more complex. Now, if you look at the amount of energy, these large molecules, they will have way more energy than these individual molecules. So this will be endergonic reactions, anabolic reaction. An example is dehydration synthesis. Now, catabolic reaction are reverse, right? It's a splitting of large molecules into smaller molecules. And example would be digestion or energy production. So digestion, here example, hydrolysis. So now when you need extra energy, you can use this glycogen that was stored in your liver or the ones that was stored in your muscles, and using enzymes, you can break this molecule into glucose, and glucose. And by doing it, you're gonna release energy that will be used for, some other processes, maybe for synthesis of ATP. Or you can do the same with triglyceride. You can break them back into 3 fatty acid and glycerol, polypeptides, you can break in amino acids, nucleic acids, you can break into nucleotides, right? So look, it's the same as here, right? Only we're moving in a different direction. So this is synthesis, dehydration synthesis, and this is hydrolysis. And lysis means you break something apart. Hydrolysis means you break something apart and you're using water to do it. Another example of catabolic reaction that is very critical for your survival is cellular respiration. It's an oxidation reaction. So you can see through the cellular respiration, glucose is broken into carbon dioxide and water, and oxygen is used, right? And this reaction, it yields about 38 molecules of ATP. So this reaction, catabolic reaction, is used to synthesize ATP, and ATP is pretty much like very, very important source of energy for cellular functioning. Now, rate of chemical reaction. it kind of makes sense. If you want to increase the rate chemical reaction, you can increase temperature too. So temperature goes up, rate goes up. Now, if you want to increase the rate chemical reaction, the particle size need to be small. Decrease the size of the particle, increase the rate of reaction. Now, you increase concentration of reactants, you will increase the rate of chemical reaction. Now, catalysts are chemicals that increase the rate of chemical reaction without being chemically changed. In a biology, we have enzymes. Enzymes are biological catalysts. Okay, now when we look at the molecules or compounds, we can divide them into two groups, inorganic compounds and organic compounds. And inorganic compounds include water, salts, many acids and bases, and they do not contain carbon. Organic compounds include carbohydrates, fats, proteins, nucleic acid, and they contain carbon. They're usually large, and carbon are covalently bonded to another carbon atom or hydrogen atom or some other atoms, maybe like sulfur or nitrogen. So organic compounds, they contain carbon. They also need to contain hydrogen, actually. So carbon and hydrogen for organic, and no carbon or no hydrogen for inorganic. So for example, if you have H2, right? This would be inorganic compound. It's a hydrogen gas. It's a molecule of hydrogen. It doesn't have carbon, so it's not organic. So we will talk very quickly about inorganic molecules that are important for life. So water. Water takes about 60 to 80% of the volume of living cells. It is most important inorganic compound in living organisms because of its properties. And we will not cover properties here in this chapter because it will take me another like 20 minutes to do it. It just, water is important. Salts. So salts are ionic compounds that dissociate in water. And when they dissociate in water, they contain cations other than hydrogen, H+, or hydroxide, OH-. So if you look over here, we have here acid, base, and salt. So all of them can dissociate in water. But look, if an acid dissociate, it has hydrogen, right, cation. When base dissociate, it has OH-, right, this is anion. Right, so that hydroxide ion. Now when salt dissociate, it also has cation and anion, but they not H+ nor OH-, right? This is calcium and chloride. So that's what it says, that salts, they dissociate in water and they contain cation other than hydrogen plus and anions other than OH-. Now, ions are electrolytes. So this is electrolytes, they all electrolytes. And electrolytes, they conduct electrical currents in solution. Ions play a specialized role in body function. Very important, sodium, potassium, calcium, and hydrogen. So electrolytes are actually essential for our survival. Now, acid and base. Acid solution contains a higher concentration of hydrogen. And when the concentration of hydrogen increases, then acidity increases. Alkaline solution contains bases. For example, OH-. And when we have decrease of concentration of hydrogen, then we have increase of alkalinity. So we use pH scale, right, to assess the concentration of hydrogen in a solution. So what is pH scale? pH scale is a negative logarithm of hydrogen ion concentration in moles per liters. When it says negative logarithm, it means when the number goes up, actually pH goes down. So they kind of opposite to each other, right? So let's look at it. Neutral solution. So pure water pH is neutral. So we represent this pH 7, right? pH 7 means it has 10 to minus 7 power of moles concentration of hydrogen ions in 1 liter of solution. So if you take 1 liter of pure water, and you will calculate how many hydrogen ions are in 1 liter of water, you will find it's actually 10 to minus 7 power moles. So all neutral solutions have pH 7. Now look over here. When concentration of hydrogen increases, remember when concentration of hydrogen increases, we have more acidity. So solution became more acid. So concentration of hydrogen increases, but the number for pH decreasing. And this is because, I'll go back, this is because the pH is a negative logarithm, right? So when concentration of hydrogen goes up, pH are actually getting smaller and smaller and smaller and smaller, right? That's why acidic pH is from 0 to 6.99. So neutral is 7. The smaller is your pH, the more acidic this solution is, and the higher concentration of hydrogen you would find in this solution, right? And also we need to remember that it's a logarithmic scale. So when we have pH 5 and pH 6, it's not just difference in, like a small difference. It actually has, pH 5 has 10 times more hydrogen than pH 6. In alkaline solution, when we have decreased concentration of hydrogen ions, less and less hydrogen ions we have, more alkaline solution became and pH goes up. So alkaline or basic solution pH from 7.1 to 14. So over here you can see the diagrams that show us how different products that we eat, what is their pH, right? We start with the neutral pH and then we go to the basic. So pH goes up, 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 but it means that concentration of hydrogen goes down. And when pH goes down, 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 concentration of hydrogen goes up. All right, so here lemon juice or hydrochloric acid that is found in your stomach has very, very strong acidity. And over here, oven cleaner, ammonia, bleach, sodium hydroxide, they have very high pH, so they really alkaline solutions. Okay. Now, acid-base homeostasis is critical for your normal functioning. pH change interferes with cell function and may damage living cells. Slight change in pH can be fatal. So pH of your blood plasma, of your body fluids need to be regulated. And it is regulated by kidneys, lungs, and buffers. Now, what is a buffer? A buffer is a mixture of compounds that resist pH change, right? So here's the example of the buffer that is present in your blood plasma. So in your blood plasma, when you have carbon dioxide in your plasma, this carbon dioxide dissolves in water and it forms this weak acid, right? And this is called carbonic acid. So in your plasma, you have very weak carbonic acid. But you not only have a weak acid, you also have this weak base, right? And this is called bicarbonate. So you have acid and base. It's called conjugate base. So you have weak acid, you have weak base, and you have protons, right? Or hydrogen plus ions. Now, how would this buffer? So it's all found in your blood. So in your blood, you have this carbonic acid, you have bicarbonate, and you have hydrogen ions. Now, how this buffer system help you to regulate your pH? For example, if pH of your blood plasma goes up and up and up, that means you have more and more and more hydrogen ions. So let me see if I can pick up my pen. Okay, instead of pointer. Pen. Right. So, for example, if you have increased acidity of your blood plasma, that means you start having lots of hydrogen ions, right? So your acidity goes up. Now you have a lot of these hydrogen ions. That's not good because that can kill your cells. Now what's gonna happen, then this bicarbonate gonna accept, well, you have not just one, right? You have many of them, CO3. So this one, and then you have over here, HCO3. I'm gonna take this one. So this bicarbonate gonna accept this hydrogen and became carbonic acid. So then what? The concentration of hydrogen ions will go down because you don't have free floating hydrogen ions. So you attaching them to this bicarbonate, forming carbonic acid, and you decrease the acidity. That makes sense? Now, if your blood became alkaline, then this carbonic acid dissociate and increase the concentration of hydrogen ions, right? So that's how this buffer works. So over here you can see this is normal pH level of blood plasma, and this is 7. This is the neutral. Your blood plasma is actually a little bit on alkaline side. Let me pick up my pointer now again. So your blood plasma is not neutral. Your blood plasma is toward the alkaline, right? The normal pH of your blood is between 7.35 and 7.45. And you guys do need to remember those numbers because that's very important. So it's normal pH. Now, if pH of blood plasma is below 7.35, we call it acidosis. And if it's below 7, we call it death, right? So this, you can see how important it is to keep pH in the normal range. Now, if pH of blood is above 7.45, this is called alkalosis. And above 7.8 is death again. So that's your normal range for pH of the blood plasma. And this buffer system, carbonic acid bicarbonate system, plays a huge role in keeping this pH constant. Okay, so this is where I'm gonna stop for the first video lecture because we covered so far. Let's just quick review it. We talked about this is matter is made of elements, and elements are made of atoms. And your elements in your body, 4 of them, 96% by ions. These elements can be trace elements, And then we said that those atoms, the elements, they can interact with each other. Interaction with the atoms is called three types of bonds, right? So, and then so we talk about bonds, ionic bonds, hydrogen bonds over here. Really, they can be exergonic and endergonic, and then endergonic reaction, anabolic reactions. So we do something, exergonic reaction, reaction to break large organic molecules, and then mention water, so and and base. And we kind of like it to keep it's constant. In the next, we have our organic bases. So thank you for watching, and I hope it was helpful.